Hello, folks. Welcome back. Today we're going to be implementing term frequency inverse document frequency. That is TF-IDF. And of course, that's a method for creating a representation for text or generating embeddings. Now, in our case, we're going to have a set of documents and we're going to generate embeddings for that. So we're going to have representation of the documents. I have prepared the like a layout or a skeleton for this implementation, and as you see, we have the function signature right here, and I also have the evaluation code. So we're going to be testing our approach against that of sklearn, and if our approach is kind of very close, or the embeddings that we produce is very close to the embeddings that sklearn's implementation produces, then we're going to call that a good implementation. Okay, so to do that, again, we're going to basically take in a set of documents and produce embeddings. Now, I do have a function signature here, but I'm thinking perhaps we're going to actually simplify that a bit. We're going to come back to that signature later on, but for now, let's simplify that. Okay, so we have a set of documents, so that's what basically the signature says. It says, I'm going to take a list of strings, so that's a set of documents, set of strings, a list of strings, and then produce a NumPy end array that would be embeddings. And the number of rows in this, the number of rows we would have in the embeddings would be the number of documents, right? If you want to think about it in terms of like a matrix. So in this case, let's go over the documents first. As you see here, we have 3 documents. Again, these are kind of toy documents just to test it, have a kind of some evaluation of this. And we have like sun is shining, sky is blue, and then sun is shining and sky is blue. All of the documents are lowercase, and I actually made sure that certain words are removed from these sentences in this case. Again, this document could be very long, but for the sake of simplicity, I kept those short. And so I removed some words. The reason for that is because the sklearn's TF-IDF vectorizer, it actually does some pre-processing with text. So it may remove some words like stop word removal and things like that. It does some pre-processing, and so we're not going to do the pre-processing. If you want to do it, you can. Perhaps I'm going to leave that as an exercise. But today we're going to be doing like the TF-IDF, the core of that, and how that works. Not even the core, the actual implementation of TF-IDF, but not of the TF-IDF that sklearn has, which does a bunch of pre-processing, but the TF-IDF algorithm itself. Okay. All right. So to do that, let me actually. I think that might be helpful. Let me comment all that out actually, and for now, let me do this. The reason I'm doing this is later on. I'm going to return some intermediate results and highlight what we got. All right. So with this implementation, I also want to mention that I do expect that you do have some understanding of TF-IDF. But even if you don't, I think it's not going to be a problem if you kind of follow along. And I'm going to try to make sure that it's kind of easy to digest. Okay. So, and the algorithm itself is not too too difficult, so nothing to be afraid of. So let's go. Now we have again 3 documents in this case, but it could be n documents and of arbitrary size. Okay. The first step that we're gonna take here is that we're gonna find the number. We're gonna find all the unique words. Okay. Unique words. And I like doing this using a set comprehension, but let me show you how this is. Well, let's do it this way. So I'm going to show you the set comprehension first. If you don't know how set comprehension works, pretty similar to list comprehension and dictionary comprehension as well. I guess with the dictionary comprehension is about pairs. In this case, we don't have pairs, but yeah. So what we need to do here is that for this is pretty much all the unique words right here. Now, if you don't understand what this does, I can also show this to you. But again, I expect you to know this kind of stuff. So this is basically a very simple thing here. So this right here is this. You can think of it as pretty much these 4 lines. Okay, and if you actually look at this closely, you're going to see that's it looks actually very, very similar. So how can I get to this from this? Okay, let me do some copy pasting. I'm going to copy paste this here. Okay, just copy pasting. Then that I'm going to copy paste here, and then I'm going to just add that. They look the same, right? So it's pretty much, this says that give me a word for doc and docs and for word and doc.split. So that gives me all the unique words. And doc.split, why do we do this? Well, because in this case, we assume that documents are just, the words in documents, they're separated, or the terms are separated by a space. If it's something else, you would have to handle it differently. If it's a tab, you handle it appropriately, you split on tab. If it's either a tab or a space or something else, then of course you could use a regular expression or something else, or to a split, multiple splits. You could have a state machine. There are different ways to do this. But again, for the sake of simplicity, let's assume that we use a space as a separator. So we get all the unique words. The next step is producing an index for every unique word. And we're going to see why that's actually useful. So it's like a word to index. Let's call it that. So for every word, we're going to have an index for index and word in enumerate unique words. And that's a dictionary comprehension. So using a set comprehension and a dictionary comprehension, we got a lot of kind of useful. You could call these like utility data, whatever. Some basically a lot of helpful data here. All right, the next step is generating what's known as the. These are like term frequencies. So it's you can call it term frequency matrix. So the idea here is that it's initially, and again, I'm going to show you what we got. Actually, let me first return unique words, run this. We have sky, sun, is, blue, and shining. These are unique words across all documents, and you can see it here. And word to index is this. So every word, every unique word has an index. The next step is producing, again, term frequency matrix, and that's actually pretty easy to produce. So we're going to iterate over the documents, and within every document, we're going to get words. Within every for every document, we're going to get we're going to iterate for every document, we're going to get all the words, or iterate over those words. And then we're going to need the document index as well, actually. And a document index, basically the term frequency, we index into it using document index, because that is like the first dimension, and then because we're iterating over the documents, we index into it. And then how do we get the word index? Well, that's where this word to index utility data, whatever you want to call it, comes handy, and we're gonna give it a word. And let me show you what this does now. So it basically gives us, and let me actually also show the. Let's not hide that. So we have, again, 3 documents. So we got three rows here, and for every row we have like a count of a unique word. In this case, let's say I don't know, sun is shining and sky is blue. In this case, I expect to have one of the positions, one of the slots, as 2, because we have 2 words, 2 occurrences of a word is. So here we go. Sky is blue in this case. I expect just 3 ones. 1, 2, 3, yeah. Sun is shining. I expect, again, 3 ones. There we go. So that's pretty much what a term frequency matrix is. It basically shows the term frequencies. It has the term frequencies for every document. The next step is producing what's known as the document frequency matrix. We can call it document frequencies or document frequency matrix. The document frequency matrix it's basically how many. Let's say we have a unique word. Let me show you here. Like is a unique word. How many documents contain this? So basically, what document frequency matrix tells us is how many documents contain word is, for instance. In this case, the answer would be 3. All 3 contain that. The document matrix would also tell us, or document frequency matrix would also tell us how many documents contain word sky. In this case, 2. How many documents contain word blue? Also 2. How many documents contain word end? That's 1. So how can we do that? Well, let's get back to this return TF. So we have this, right? Well, when does a document contain a specific term? Well, when the count is not 0, right? So if the count, as long as count is not 0, we say that there is this word, and across the rows or every column here basically is the same word, right? And so, for instance, whatever this word is, seems like the first and third, or index 0 and index 2 documents contain that, but index 1 does not. And we know that true that's is, because that's the only term that occurs in all of the documents, and we see that it occurs everywhere. And then we need basically the counts for these. How can we get the counts? Well, we need to sum across the rows. So that's what we're going to do. And there we go. 2, 3, 2, 2, 2, 1. So 3, again, it's is, and the rest of those 2, 2, 2, and then we get 1 for end, because that occurred only in the third document. So that's the document frequency matrix. Okay. Now, if you're wondering how did that even work, we had like trues and false, and I just summed it over. How does that work? Well, Python has this thing where if it's a Boolean true, it's 1. If it's a Boolean false, it's 0. So true plus true, that's 2, and false plus true, that's 1. Okay, so that's why it kind of worked that way. So true plus false plus true, that would be 2. Okay, so that's why it worked. Okay, so we got the document frequency matrix. The next step is producing what's known as the inverse document frequency, and we're going to use the document frequency for that. So IDF. IDF. There's actually, there have been discussions on whether inverse document frequency is needed. Some people argue that it's not needed. Some people argue that there are better approaches. I'm not going to go into that in this video. We're just going to implement TF-IDF and have some intuition on how it works, and also know how to implement it, right? So, but just so that you know, there have been discussions, and I don't know if people actively discuss this today, because we have embedding-based, transformer-based models these days that do that, and perhaps up-and-coming state-space models, maybe that's to come. So those discussions, I'm not sure again if these discussions are ongoing, but there have been discussions in the past. Anyway, so we have document frequency matrix. Let's have the inverse document frequencies now. Inverse document frequency is basically length of the documents over the document frequency matrix plus 1. Okay. Well, it's basically document frequency matrix multiplied by 1 over a length of docs. But we can write it that way as well. And TF-IDF, it's just the term frequencies multiplied by inverse document frequency and just return that. And that's pretty much it. We just implemented TF-IDF. And there we go. We got representations for every document. Now, we want to make sure that whatever sklearn has, we can reproduce that. So our this check basically here, it kind of makes sure, as I said, that our implementation and sklearn's implementation, those are close. And I sort our representations because I don't know what order sklearn does this, and I think that they might also be using this kind of a set that in Python these days set ordering is preserved. So I'm not sure if sort actually is needed, but I just put it there just in case. Now let's run it for now. Okay, we got assertion error. Okay, so to get it basically very close, or to have pretty much the same implementation as the default, sklearn's implementation, we have to add a few parameters to this. And sklearn's implementation has a lot more, parameters. And so what I did is that I removed this now, and we go to this other kind of function signature. So we have two more parameters. First one is smooth IDF. Smooth IDF, I don't know, it may sound a bit exotic, but it's a very simple thing actually. So if not smooth IDF, let me do a ternary if in Python. So we're going to use this if not smooth IDF. So if that flag is false. By default I set it to true. So we reproduce whatever sklearn has. And if it is true, then here is how it's different. I just copy whatever we have, right? We just add 1 to both numerator and denominator. That's it. So let me repeat this. I copy that over, whatever we have here. Exact same thing is here, right? And I just add 1 to both the numerator and the denominator to smooth things out. That's why it's called smooth IDF. And that's pretty much it. And we just need else here. Okay. Now, so that's smooth IDF parameter, and the one that is left is normalize. So normalize is even simpler, actually. Well, both are, I guess, simple. Normalize, it's basically a L2 normalization. So if normalize flag is on, we divide TF-IDF by the norm of TF-IDF across the first axis, and I think we may have to do this. Oops, has to be the other way around. We may have to do this, otherwise, let's see. So let's remove this first. Okay, yeah, shapes won't match, but if I do this, so the NP new axis is same as none. We have to basically do this so that the shapes match. And now we don't get the assertion error. So this is the implementation for the TF-IDF. That is the term frequency inverse document frequency. And actually, in one of my papers, I used this to generate embedding, so it's not too bad. And overall, it does not really use a machine learning model to produce embedding, so it's kind of exact. We don't really have we don't really use we don't really have any random initialization or anything like that. It's kind of like a deterministic algorithm, and so or at least you can make it deterministic. Of course, if you add some some steps, shuffling and if you customize TF-IDF, you can make it. You can make it so that it's not deterministic, but yeah, it's kind of an efficient algorithm, or you could perhaps call it a model. We could also implement it as a model, by the way, just so you know. I could have done this from data classes, import data class, and I could have done, data class where you have a TF-IDF like that, and that perhaps takes smooth IDF, by default that's true, and takes normalize, by default that's true, and then perhaps we have like a fit, and what fit does is maybe it takes the documents string, and perhaps it does not really return anything, it just fits, and then fit transform, it uses the parameters that we got here. So perhaps we a fit transform fits and transforms at the same time, and then perhaps we have a transform. So fit transform would just do self.fit on docs and return self.transform of docs, and then this would return np.nd arrays. So, and in a fit, we would perhaps just produce term frequency matrix. I believe we could just produce a term frequency matrix in this case, and then for the rest of those, compute other parameters and do multiplication, or well, in the fit perhaps we compute unique words and word to index. I think that would be a more accurate, and the rest of the stuff goes into a transform. There are different ways to implement this, basically. That's what I'm trying to say. And I think implementing it as a class is probably a better approach. But the previous video, we implemented PCA as a function as well. So perhaps I'm going to have a video where we make classes out of this, and we would have layout similar to this. The skeleton and the way they would work, and this would of course return an np and d array. So yeah, that's going to be it for the video. I hope you enjoyed it. I hope you learned something new, and I now hope that you know how to implement TF-IDF. So I'm going to see you in the next video, and yeah, if you have any comments, feel free to comment in the comment box, or below the description box. So thank you.